So, can I speak in French? No, I'm kidding, So, in order to continue what Wendelin presented on SLE, I'm going to introduce the notion of spanning tree, and connected to this notion, the notion of space filling curve. So, and then I'm going to show the idea, so how to prove that the space filling curve connected to 2 points of the boundary of a domain is going to converge to the SLE 8. So this is the same idea that we already view with Wendelin. We need to find an observable that is conformally invariant. So we are going to get this observable conformally invariant using an algorithm that I'm going to introduce, which is a Wilson algorithm. So first I'm going to show quickly how spanning trees are related to the FK model by taking a limit. So we are going to show that the probability on the FK model, when we take the value of P, which is the safe dual value, converge to the measure over all spanning trees. So I'm first going to make this. So I remember that I recall you that so first thing I'm going to do is FK connected to spanning trees. So we take G, a subgraph of Z2 connected, finite. So we don't have any problem to define the FK model on this graph. And I recall that the probability we use is a function of two parameters, P and Q. And we have, so I can write it this way, we have a constant of normalization. And I'm going to write it like this. So here I denote the number of open edges, and Q is to the power of the number of connected components, right? So I'm going to take a particular value of P, which is the safe dual value, which is a square of Q over 1 plus square of Q, which is the self dual value. And with this value of P, the question I'm asking is which is the limit when Q tends to 0 plus of this measure, right? So I'm going to show quickly that we get a measure over all the uniform spanning trees we can form on G. So the first thing, so I can first say quickly which, so in this case, the measure we get with this particular value of P is the following. So P over 1 minus P makes exactly square root of Q. So we have the constant here. And we get Q to the power, so we have open over 2 plus K, right? And the constant Z is the sum over all the configuration of this quantity. So in order to understand what's the limit of this probability when Q tends to 0, we need to understand what terms will be preponderant in this sum when we let Q goes to 0. So to make this, we are going to see that in fact O over 2 plus K will be minimum when we get a spanning tree, when omega is a spanning tree. So we are going to show this quickly. So let's try to understand first what's the value of this quantity for the different possibility of omega. So the first case is when omega, let's say, is a forest. So when omega is a forest, we have, let's say, G trees. So what's the value of this quantity. So how many open cluster do we have? So let's say we have n site, which is in G, right? So how many open edges do we have when we have G trees in our graph? So in fact, for each trees, let's say they are all of cardinality, let's say K1, Kg. So clearly we have the sum of the Kg, which is of the Ki, which is equal to n. We have all the sites, but the edges are connecting the trees like this to make G trees. So for each tree, we have exactly Ki minus 1 open edges to form a tree. Because when you have a tree, you can make a simple path like this. So it's clear you have exactly this. So the number of open edges in this case is exactly the sum of the Ki minus 1 over 2 plus the number of components, which is in this case G. So in this case, we get exactly, so here we sum this, so we get exactly n plus G over 2. So here G can take all the value, 1, 2, 3, and all this. So it's minimum for G equals 1, which is exactly the case of the spanning tree, because we have one connected component, which is a tree. So this is exactly the definition of a spanning tree, right? So now, let's try to understand in the general case using this one. So when W, let's say, has R faces. So the previous case was only one faces, in fact. We have no loop, right? No cycle. So we are looking to a configuration that has R faces. So I claim that we can delete R minus 1 edges and obtain, in fact, a forest with the same number of connected components. So you can get this by induction. Right? So if you have R faces, you take off an edge, you delete a face, and doing this R minus 1 times, you get a forest. This is quite clear. So now we can use the previous result to try to evaluate this quantity. So how many open edges do we have? So we have exactly, say G, the number of components. We have n plus G over 2, which was the result for the previous case. But we need to add the R minus 1 over 2 edges that we deleted to get this result, right? So here, G maybe is 1, we don't know, but we know that R in this case, because this is the, we want to go, we already treated the case R equals 1, so R is bigger than 2. So in this case, this quantity is, let's say, strictly bigger than n plus 1 over 2, right? So we have treated all the cases, and we now understand that this quantity is minimum when we only have one component with one face, which means that we have a spanning tree, okay? So the conclusion of this is that when you look to the constant of normalization Z, and that you make Q tends to 0 plus, you have all the terms that correspond to spanning trees, for which you have q to the power n plus 1 over 2, donc the number of spanning tree. And the other terms are, it's a sum of q to the power something bigger to this quantity, because this is what we show. So we have exactly this equivalent, right? This is what we show. As we understood that this exponent is bigger for the other cases, it's small o of what we get for a spanning tree. So we have this equivalent. So now we can get the limit of p for a configuration omega. And we get directly that this quantity, as q tends to 0 plus, is 1 over the cardinality of spanning tree, all spanning trees, if omega is a spanning tree, right? And the other case, we get 0, because we get a term that has a power here bigger than the case of spanning tree, so it tends to 0. So we have the result I announced. This is that this measure tends to the uniform measure of spanning trees, right? So this was the first part of my speech about the link between the FK model and the spanning trees, right? So now I'm going to introduce the notion of loop-erased random walk in order to then introduce an algorithm, the Wilson algorithm, that can produce some spanning trees over any connected graph G. Okay? So let's now introduce the notion of loop-erased random walk. So if you take, let's say, any sequence, so this is the definition of, this is the general notion. So let's say this is the definition. If you take any sequence x equals to x0 at xm, you want to, so this is the sequence, right? And you want to erase the loop of this sequence. So you put, so Lx for any sequence will be the loop erased random walk of x. Right? So the first thing is to start at the same point as x, L0 equals x0, and then inductively for all g, consider the last time you pass through the previous value Lg. So let's say this is the max of the index, such that we have so this is the last time the sequence pass in the previous value of the loop arrays we are constructing, and you put the next value of the loop erased walk, which is the next value of the sequence you initially took, right? So this is the natural way to erase the loop chronologically. So let's say the number of steps of this, we are going to introduce notation. The number of steps will be denoted by sigma, such that, in fact, you always finish your loop erase by the same value of per sequence, right? So this is not fixed. This is something that can vary a function of the sequence you take. Okay, so now we already defined the notion of loop erase random walk for any sequence x. Okay. So now, let's make some remark about this notion. So we're going to more or less prove a type of Markovian property for loop erased random walk that you get with a Markov chain over, say, countable space. So let S be a countable space. So this is the state space of your Markov chain. Xn be recurrent, let's say, recurrent Markov chain over S. And we're going to take a non-empty subset A of S. So let also tau A be the heating time of A, which is almost surely finite because we have something recurrent. So we have a set A here. Let's say that x0 is a value x fixed. So we start here. We are making something. Oh. Eventually we are making loops. And we then get into A. Okay? So let's denote by L A the loop erased random walk of the Markov chain X up to time tau A, right? So we're just making this and we delete the loop to make a simple self-avoiding walk up to A. Okay. So the property we want to get, so I'm introducing this property because this is something quite natural and it will allow me to introduce some tools for the demonstration of the Wilson algorithm. So the Markovian property we want is the following. If you take some points, y0, y1, up to yg. So let me introduce another definition here. So denote also, I'm going to denote by p, x, y, a, the law of the loop erased we get, starting at x, because this is what we were making here, conditioned on the fact that the last value taken by this loop is exactly y, which means, well, when this is of probability strictly positive. Okay? So we condition a priori LA can get any point of A accessible, right? So we are conditioning on the fact of hitting A in a single point Y. So we denote this measure by P, X, Y, A. This is the law condition on this event. Okay. So the Markovian property we want to get is in fact the following. Let's imagine y0 is here. Here we get this one. Okay. This is A. So we let our random walk evolve. We loop erase all this. And in fact, we want that the law, I'm going to make grow the subset A I've taken before by adding this set of points, right? So I'm going to ask that the law of the loop erased starting in X up to condition on the fact of hitting this point. So I'm going to write it, this will be more clear of what I'm saying. So are the notations clear here? Yeah? Okay, so I'm going to write the following. So the law of the loop erased LA up to time sigma minus G, which is exactly this orange part, conditioned on the fact that we already know the last value of the random walk, which is we ended here, but the previous one was y1 up to the other one was yg. So the law of this part, conditioned on the fact that we know that the loop erased is coming here, is exactly, with the notation I already introduced, the law of the random walk starting at x, conditioned on ending at yg, up to the time hitting this growing set. Okay? So this is something quite natural asking this, because after this we can define in the other way the loop erase random walk starting by here, and we have the same kind of property in the other sense. So this is what we are going first to give the key to demonstrate this. So here's the statement of what I'm saying here. Yeah. So in order to get this, let's directly calculate the probability of the realization of any sequence for the loop erase random walk. So we take W, W0, Wn, so this is x in fact, because we want to start in x. This is any point of A, and the other one are not in A. So let's calculate the probability that the loop erased so we take a self-avoiding path. Okay. So how to make this? So what is random in this realization of the loop erased is what can do the initial random walk between all the point W1, W2, and so on, which means that it can make loops. So the first loop, we make some loops over W0. Then we go to W1. And then we can make other loops, but we can't go back to W0. So we make the loops over W1. But we can't go back to W0. And we are not hitting A also. So at the second step, we are not hitting A and not hitting W0. So the next step, we get to W2. We are making loops. We can't go back to W0, W1, and A. So we are making grow the set we can't hit, and we are still making loops like this. So in fact, we can decompose this, for example, with all the realization of the random walk. So we will going to ask, so we take all the sequences such that when we erased this sequence, we get W. So this is deterministic. And we check the probability that the loop erase random walk of X is equal to the sequence we are taking. Okay, so in fact, I'm going to let this as an exercise. So as I told you, we have W0 here. Then you have W1 here. You're making some loops. Then you go to W2, W2, and so on. So there is a quantity which is important in this statement, which is the number of visits you are making on any point W. That will be important for this quantity. So let G, let's say, XA be the expected number of visits of the random walk in X starting. So we start at X. We start at X. We count the expected number of visits in X before hitting the set A, right? So we already understood this is a important quantity in our problem. Right? So, as an exercise, you can show that this realization is exactly, so we start at W0, right? So we want to know how many loops we make before hitting A. So we have this quantity that is going to appear. So we count the number of loops. Then we go, so let me introduce one more notation, which will be the transition probability of the Markov chain. Let's denote by P, X, Y, the transition probability. So which is just the probability that when you are X, you how many probability you go to Y. So then we have to go to W1. So we will have this quantity that's going to appear. We count the number of loops, we go to W1. And then we are going to make some loop in W1, not going in A, and not going in W0, right? This is what I was saying. So this quantity is also going to appear. And then we want to go up to W2, and so on. So finally, we have the number of loops we make in Wn-1 without hitting A and without hitting the other points. So this is not clear that this formula is true, but it is. And we are now, we counted the loop making on this point, so we have now to go to the last point of the loop erased, which is Wn. Okay? So I claim this is true. So let's introduce now a function f, which will be the produce of all these quantities. So, I mean, don't focus too much on the details of this proof, but just concentrate of this function I'm going to introduce, which will be the good instrument to show Wilson algorithm. So let's define understanding the feeling of this proof. So let's define this function f, which will be the product of all the quantity g introduced in this product without taking count of the transition probability. So this is expected value of number of passage on W0 without going to A, then of W1 without going to A, neither W0, and so on, up to W minus 1 without going to A on the other point. Okay? Right? So this quantity represents more or less this, but without saying how do you go from W0 to W1, W1 to W2, and all this, right? Okay. So keep in mind this. So now we want to get some property of this function f, and the property we have, in fact, is that this is symmetric on the argument, on the n first arguments. So to get this, one can show that, let's say this is another exercise. For any point you take y, y prime, and let's say a prime, you can permute in G. So you have A here, A prime. You have a point here, another point here. So what I'm going to say is that if you count the number of loops you make over y before touching A, and then the number of loops you make over y prime without touching A and y, this is the same quantity as starting in y prime without touching A prime, and then going up to y, making loops without touching y prime, right? So in some sense, you can permute the variable y and y prime by making this in a clever way. So we are just asking to make loops here, and then not touching, coming back here. So this is quite intuitive. Okay, is this statement clear? So this is exactly what we need to get the symmetry of the function f in its n first variables. Because if you want to permute, let's say, the gif and the if, so you make a certain number of transpositions like this, of small transposition, by using this lemma, and you can switch to variables like this, and by decomposition of any permutation, you get the symmetry of your variable f. Is the idea clear of this proof, right? So with this, you get that f is symmetric in its n first variables. Okay? Bon. So, okay, let me just come back to what we did. So we just first calculated the probability of the realization of the loop array's random walk to be such a sequence. So to get this, we obtain that this is the product of a function f, which is symmetric in its variable, times the different probability of transition to go from one point to another. Okay? So now with this, let's try to compute the fact that the conditional law is what we want. So I'm going to make the case G equals 1. So the first step of, I'm just going to add 1 point to the set A. So fix, let's say, y0 and y1. Okay? So this will be two fixed points, so where we want to reach A and the point we want to have. So x is also fixed, and the variables will be the other points. So we have x, we don't put it here. So then we have w1 up to w, let's say this is un, n minus 1, so n minus 2. Then we have y1 and 0. So this is the, which is variable in our case, right? So, okay, let's calculate it directly now. So let's calculate the probability that the loop erased random walk. So up to time sigma minus sigma is n, right? I'm sorry for this. This is the number of steps we have. So that this sequence be equal to x w1 up to so we finish at y1, right? This is right. I think so. Okay. Conditioned on the fact that we know that the last point was y0 and the previous one was y1. Right? This is what we are interested in, because we are interested in the conditional probability that we have here in the case where g equals 1. So we are calculating the probability. So we want to know this law. So we just take a realization of this event, of this, so we take a realization we have here for any w1 up to wn minus 2. Condition on the event we are interested in, and we want to make appear the other probability p we have here. So this is what we are going to make. So as we claimed before, we already know almost everything in this, because we know that the probability we have up in this condition probability is exactly the f. So let me be consistent with all this. So the first point here is x. Then we go up to w1. And we go up to n minus 2. Then we have y1, which is wn minus 1, let's say. And we have the transition probability. So we start at x, we go up to w1. Then we have n minus 2. We go to, this is product, all this, right? Here you have product also, going from y1 up to y0. And you have to divide this by what we conditioned, which is the probability that the two last points are already known. So, which is this. Right? Okay, so now almost everything is finished. So this was the difficult part of the proof, introducing all the notations. So now we have that f is symmetric in its variable, so we can permute all this. So let's say we are going to put y1 in the first variable of f. So doing this, we are going to be able to isolate y1 from the other point and to make appear the quantity we want in the condition probability here, because we are going to add y1 to a if you think about the definition of the function f, because here this will be y1 that will appear in the set a like this. It will be added at each step, so it's going to make appear what we want. Okay. So I'm going to permute this variable and reuse this expression to show you that we have what we want. So I'm using the same expression, right? So I come back to G. So the first part is G of y1 up to a divided. So I'm going to isolate now all this what is constant. So I'm going to take the transition probability, this one, and to divide by the other probability already introduced, which is this. So this is a constant because we already fixed all these points. Okay? Times all the rest. So what do we get? G. So I was permuting the variables. So now the second one is x. So I need to put in A the value of y1. So I'm making this for all the j. And the last one I get is, let's put it backwards here. Okay, so I'm sorry, this is not very times g. So the last value we have is now w n minus 2 a. So we first added the y1 point, but we continued added points. So we already added x here after. So after this we added the w1 point up to the w n minus 3 point. Okay. And we have to put the other condition, transition probability, which are the following probability of. So this is a bit calculating, I'm sorry. xw1 up to, so I'm in w1, then I want to go from n minus 2 up to y1. Okay? So here we have a part which is, let's try to understand this, as we already introduced all the function we are using. So this is, okay, this one also. This is a constant, forget it. Now look at this one, this part. So, G counts the number of loops we make. So we start at X. We count the number of loops without touching A and Y1. So let's imagine that A and Y1 are the new part. It's A prime, right? This is the new set we are going to reach. So we make a number of loops. Then we have the transition probability to go from X to W1. So we are now in W1. Then, which is not written, but I can written here, we are in W1, which is the other products we have in F. We count the loops without touching A and Y1, but without touching also the point we already considered, which is X. So we were in X. We counted the loops without touching A and Y1. We go in W1. We now count the loops without touching A and Y1 plus the last point, which was X. And we also have the products of all the transition probability we have. So we have everything we need to get exactly this probability here, to be conditioned on the fact of finishing on the point Y1 without touching A union Y1 and counting making the loop erase random walk. So this is all I have emphasis here, is exactly the probability starting at X, ending in Y1, before hitting time of A union Y1, right? So what do we do with this constant now? We just claim that this is 1, because we have two probability. We have a condition probability here, which is equal to another probability times a constant. So this constant, by normalization, is 1. So we don't care about it. Okay. So we have what we wanted. Okay. So this was the technical part of my speech, if I can say this. But it was useful to introduce the function f, as we are going to see, and the fact that this function f is symmetric in its variable. And we have to keep in mind the signification of f, which is that you count the number of loops, you go back, you don't care about the other point, you count the number of loops and all this, right? Without knowing how to switch, how to go from one point to another. Okay, so it is more or less clear. Okay. So now we have almost everything to. So let me remember you that we were working on spanning trees, which are connected components with only one face or without cycle of a graph. So we have a tree that takes all the points. that go up to every side of the graph you have. This is a spanning tree, right? And now we are going to introduce an algorithm, which is the Wilson algorithm, that can produce randomly such spanning trees. So I don't know my numeration, but let's say this is true, I think. So we want an algo that produce spanning trees. Uniform. Okay. So take a graph, a finite graph, finite subgraph. We get the same. We are working with the same objects. Connected graph, finite. Okay, so we have G here. So we can you can think this in terms of percolation stuff. I mean, this will be we will let the grid tends to 0 after this to get some SLE property. So this is the same thing we already made with Wendelin. So we have Z2 here. And we want to produce some spanning tree inside this graph. So the idea of this is to say, okay, let's take any ordering of this graph. I give a name to all the points. I take all of them, the vertices, right? So I take all the points, all of them. And I want to create a tree. So we understand that the notion of loop self-avoiding path obtained by loop erased random walk may be useful to create this, because we are making no cycles, so this is useful for the trees. So imagine you start your loop erased random walk in V1. So you make loop erased up to the moment you hit this one. Okay? So this will be the first part of our tree. We took any ordering of G. V0 is fixed, it's here. And we start from V1, we make loop erase up to V0. So we get the first part of the tree, I claim. Then I start from V2, and I'm going to make a loop erase random walk up to the hitting time I'm reaching what is already created. Okay, so I make another loop erase random walk up to the moment I'm reaching what I already created. Okay, so there is no loop because we are making a loop erased, and we start at the first time we reach what we already have, which already has no loop, so there is no loop. So then I'm making the same stuff starting from the next vertices, V3, so I'm coming here. Maybe I'm going through V4, but I'm stopping at the first time I reach either the white one or the orange one. This is what we already made in the past. So we already have, again we have a tree. And then I start from V4, a loop erase random walk up to the time I'm already, I reach what we already created. Okay, so in this case, I'm already on what we created, so I'm making nothing. So I'm not making any trouble for my tree. And then I take the next point, and the next point, and the next point. So at each step, we have a tree. And as we took all the points of G, V0 up to Vm, and we are starting the loop erase, starting on all of those points inductively, we are connecting all the points. So at each step, we have a tree, and we are making this up to connect all the points. So we get a spanning tree at the, we actually get a spanning tree at the final step. Is this clear for everybody? Right. So this is Wilson algorithm. So let's make it properly quickly. Let's say take an ordering, a fixed ordering. V0 Vm of G, of the vertex of G, the vertices. Okay, and define inductively so A0 will be the first set we had, V0. And for all G positive, define gamma G, the loop erased random walk starting at V plus 1, G plus 1, ending hitting what we already get, which was in this case AG. Right? And then define AG plus 1 as the union of what we get initially plus the random walk we are making now. So we have that AM, which is the last one, is a spanning tree. Okay, so this is Wilson algorithm. But I was saying here that we want to make this uniformly. What does it mean uniformly? That just means that we have a certain set of uniform spanning trees of the graph, and we want to be able to take them uniformly with the same probability, right? So now we have to prove that this algorithm is taking them uniformly over all the spanning trees we have of the graph G. So let T be a spanning tree of G. And yeah. Okay. In fact, we are making, you're right, we are making a random walk, a simple random walk. So you look to all your neighbors and you go uniformly to each of them. You're right. So I need to precise this. Loop erase, so which is the simple random walk. So which means that if you are at point, let's say V, you have a degree, which is the number of neighbors. And the probability to go to any neighbor is 1 over the degree. So which is 1/4 in the Z2 and all this, right? You're right. So let's try to compute the probability that the tree we are making, the spanning tree we are making, to be exactly the fixed tree we have fixed. Okay. So here we have a tree T, and we want to evaluate the probability that we get this one. So in order to make this, we are going to reuse the function f and use the symmetry of f to obtain this result. This will be the key point of the demonstration. So let's try to understand how we get how to evaluate this probability. We started in V1, and we made a random walk up to V0. So in terms of function f, this is exactly, if we cut this piece of the tree connecting V1 to V0, the probability of the realization of this part of the tree is exactly the function f, okay. Oh, this is not clear what I'm saying. So let me give another ordering of the points to understand this clearly. So let me call this one so I'm going to make a permutation of the vertices given a new ordering function of the tree. So I'm going to say this one is the new first one. This one is the new second one, right? So I'm going backward like this. Say first, second, up to this one, which will be, let's say, E1. Okay? So I'm going to take, so the permutation I have here is function of the tree I'm considering, because I'm using the path inside the tree. So I'm going to give another ordering of the points, but using the tree I was considering. So the probability, the first part we have is, let's say, starting in V1, then V sigma 2. So let me put this down on the blackboard and then explain what I'm saying. Times the probability of the transition of we have. Okay. So I'm saying that the probability of the realization of the first part is exactly, you are here, you make a random walk, loop erase random walk up to V0, and then you are here, you make a loop erase random walk up to here, and then you are here, you make a loop erase random walk up to what you already have, and you make it up to this part. So this is the probability of the first piece of the tree. And then, so this is exactly what gives the function f, right? So you are on the first, you go to the next one. Then we took it from V2 up to what we already had. So we are going to make exactly the same numeration here in order to define the permutation we are interested in. So let's say this is V sigma, so we already have E1 point, so we had one, up to the other one, backwards, which will be sigma, let's say, E2. So then, to compute the rest of the probability, we have to calculate f, starting in V sigma E1 plus 1, up to V sigma E2, stopping when we already reach what we get, which is exactly the set of all the other vertices. V0, V sigma 1, up to V sigma E1. Right? So we are making the same reasoning. Now we look at this point, we make the loop erase random walk up to this point, and then we're going back to this point, and all this going backwards up to V2. And this is what gives the function f. So we have to add the transition probability to this quantity, which is the product over another time. We have another set of indices here, which is the transition probability going to one to another vertices here. So making this, all this, up to all the vertices we have. So in fact, we are introducing here, to understand this is right, a permutation sigma function of the tree, a priori. So using the form of the function f, which is a product in which we had successively some points to the last variable, we can understand that the big product we are writing here is exactly only one function f, starting in v sigma 1 up to v e1, and then we have put everything we have here inside the set we don't want to reach, and then we are starting another time here, but we already have everything we had before on the set we don't want to reach. So we can mix all the function f to get only one function f, which will be this one, and then we start to the next point, up to the last part of this branch, and then we go up to the last vertices we had, which is maybe this one. We only have to put here v0 times all the transition. So we also can make only one product with all the transition probability, which actually will get the product for all the vertices ordering this, but this is a product which is commutative, so we only have this here. Okay? But f is symmetric. So, a priori, we had a tree, T. We construct a permutation sigma function of T in order to express the probability to get this tree. But as f is symmetric, we can take off this we can take off this permutation. So in fact, the probability to get such a tree is f of v1 up to vm, stopping in v0, times the probability of all the transition, which is uniform, independent, uniform in T. This clear? So here we more or less, so you have to convince that all this is working, but this is well working to take the permutation. So the construction of the permutation is clear. Take the first branch, you order backward all this, take the second one, you order backwards, and you use the function f we introduced to express the probability. Okay. So this demonstrates that the Wilson algorithm gives uniformly a random tree using loop erased random walk. So now I'm going to finish by giving heuristical arguments to understand, to link this to SLE problems. So there are two things in SLE we can make with this, which is you take a loop erased random walk starting to one point of the boundary up to the other one, and to show that this is going to converge to SLE2, only the loop erased random walk. And you can also, using uniform spanning trees made by loop erased random walk, construct space filling curves, which is what I'm going to speak about, starting from one point up to another, and show that this converges to SLE8. So let's try to give some piece of the proof for this. So link with SLE8. So let me quickly introduce the link between uniform spanning trees and space filling curves. So take, let's say, a domain D, and open the edges on the one side of the boundary. Let's say this is the point A, this is the point B. And close, so which means you open in the dual graph. Close the other one. So I'm just opening the edges on the border of my domain between A and B, which is the same idea we already made with exploration process. And all this, we open one side and we close the other one. And okay, so let's take a spanning tree. So we conditioned on the fact this is open, but we can take spanning trees in this. So I'm sure my picture will not be very nice, but I'm going to make it as nice as possible. Okay, so let's say this is a uniform spanning tree of our domain. Okay. Condition on the fact we are open on this border, and automatically we get another spanning tree in the dual by just following the open path we have here. So my picture is not good. So you get the idea. Right? So once you have one spanning tree connected to this border, you have another spanning tree connected to the other border on the dual lattice. And making this, in fact, we obtain a space filling curve, which will be defined as the following. Start here, and just follow the way you have here, which means you go there, up. So I'm not going to make everything, but you got the idea. So taking a uniform spanning tree in our domain, conditioned on the fact you are opening on this part of the border, you get a space filling curve, which means you go to all the points, connecting the point A to the point B, because you are going to end up to this point. So we are in fact with, so there is a bijection with space filling curve. One-to-one correspondence, and a uniform spanning tree from A to B, and uniform spanning conditioned on the opening AB. Okay, so you have one-to-one correspondence between these two objects. Okay. So the fact is that to get the convergence of space filling curves to SLE8, as we already saw in the other proofs made by Wendelin, is that we need more or less two things to get this. So the first one I'm not going to speak here is a kind of tightness assumption to get this. So you have to study the space filling curves to get this. So you can show there is some good properties. And the other one, which is useful, as we already saw in Smirnov on easing proofs, is to get an observable, which is conformally invariant. We always use this. So using Wilson algorithm, we are going to show that we can get the good, the observable that will be used in the proof. So we are going to show this, the idea of this. So the observable will be the following. Take your domain. Take a point C here. So you have the other border here. And take a point, so you are on delta Z2. Okay. And the event you are going, so you take a uniform spanning tree or a space filling curve, which is the same as we said, and so you have stuff like this, right? And the event you are asking is the part of the tree touching Z is connected to CB. Because a priori, the part of the tree that touches Z may be connected to this part or to the other one. So the event we are looking at is that it to be connected between B and C. Okay? So let's try to understand the limit when delta goes to 0 of this event. So in fact, in order to understand this event, we can just use Wilson algorithm in the following way. You take Z like this, you have A here, B and C. So start a random walk from Z. So you make random walk. I'm not erasing now. Eventually, you will be hitting this part of the domain, but you say, okay, let's make a reflection. So you go backwards. Come back. Up. So what I'm saying is that when you loop erase this random walk, you will get in law, you will get the same law of the branch connecting Z to any part of this part of the domain. Because Wilson algorithm, and this is all uniform and all this. So in order to get the probability that the branch in the uniform spanning tree of D is connected to CB, you just have to consider the probability that your random walk, so we are not anymore speaking about self-avoiding path, but just a random walk, starting from Z, is going to hit CB before AC, when we make it reflect on the other part of the domain. Okay. And as we can see, because we are now working with random walks, which is a tool we well know, which is connected to Brownian motion and all this. We can show much more easily that when delta goes to 0 plus, this probability goes to the probability that on the same domain, if you launch a Brownian motion in Z, that you make it reflect on this border in some sense. You have to define some other things that I'm not making here, but making reflect, you are asking the Brownian motion to hit starting at Z, hit CB first. When delta goes to 0, this is the limit you have. And as one can show, this is conformally invariant. And you get the observable you wanted for the proof. So what we used here was, okay, we want to study space filling curves. But this is a difficult object. So we are using uniform spanning trees, which is closely related to space filling curves, as we said here. And in order to understand uniform spanning trees, we are going to use Wilson algorithm, which authorizes to use random walks instead of self-avoiding path, which is a much more simpler tool. And then, using random walks, we get this probability to converge to this one, which is the conformal invariant stuff we needed to prove the convergence to the SLE 8. So that's why we introduced the Wilson algorithm. So I think that's it.